And today I would like to speak about higher order network and dynamics. This is a really exciting work we have been doing at the interface between network science, nonlinear dynamics, and topology mostly. And so let me start. So higher order networks encode the interaction between two or more nodes, and they come in different modality. You can have hypergraph, simplicial complex, or even network with triadic interaction, on which we focus recently, and which I will discuss later on by the end of this talk. So really, it is becoming clear that this higher order network encodes the higher order interaction of complex systems. And it is becoming clear that they are very important, for instance, for studying the brain, but also beyond that for other applications. So in the brain, you might want to distinguish between three regions of the brain activated pairwise, leading to three pairwise link, or activated at the same time. And then you have a field triangle, which is an higher order interaction. Also, in neuroscience at the neuronal level, there's becoming more and more clear that the interaction between pair of neurons is mediated and modulated also by the presence of glia that can act on the synaptic signal. So this is an example of a triadic interaction when you have one node modulating the interaction between other two nodes. And in other contexts, like in social network, you have collaboration network where you know from your experience, you can collaborate with a team of scientists publishing paper with more than two authors, or you can have face-to-face interaction, or in ecosystem, you can have also this triadic interaction when a species act on the interaction between other two species, and this can be arranged in a very complex way. So you can have a triadic interaction acting on a triadic interaction itself, as in this example. So really from the studying of this higher order network and their triadic interaction, it is emerging that a higher order network theory can be really transformative of our understanding of the interplay between structure and dynamics. And if you want to have an idea of how this can be done, and very preliminary result in this direction, you can look at my book by Cambridge University Press, because this theory needs to be explored and funded. So there is it's just the beginning of I think of a very exciting new set of results on the topic. So if you want to have a less personal perspective, also a very wide overview is presented in our Nature Physics paper, including quite a lot of friends and collaborators. And here we really highlight the fact that the dynamical variable on higher order network might not only be on the node as is been modeled in network so far, but also might sit on links or on triangles. And these signals, for instance, here defined on the links, can be projected up or down to triangle or to nodes, and you can play with that. So this higher order network is a way to study generalized network structure, but of course, for people interested in brain dynamics, I think it's also important to notice that networks are being considered also to be to have a limitation, another limitation, and this limitation is that they do not account for different type of interaction, which are instead considered and taken into account in a multi-layer scenario where you can have network of network interacting with each other. And this has been widely used also in the context of brain dynamics. For instance, this is for the C. elegans connectome. It might have different layers, and you can extract more information from the study of this multi-layer network than from the study of single network in isolation. So one other research question is how we combine higher order network and multi-layer network. This is very open, but of course is important for a number of applications and in particular for the brain. So I've been working on higher order network for some time. So let me just mention a bit some results that we have done on network modelings, also because these models are important if you want to define the dynamics on top of them. So we have developed quite a series of models. For instance, something a bit like the BA model. So you have one node. Instead of attaching 3 links, it attaches 3 triangles to the network, and the triangle might be reinforced. Or you can have a triadic closure model, a node attaching to a random node and then closing a triangle with high probability. Or you can have topological move, in which you add triangle in this way, choosing a link, or just closing this kind of pie. And if you have just these 2 moves, in which you allow every link to have at maximum to be incident at maximum to 2 triangles, you get a manifold, which is a very interesting distribution of curvature, this 2-dimensional manifold. And if you have the triadic closure, you are generating a graph with community structure. And these are non-equilibrium models. So you have very simple rule to start with, and then you have this emerging phenomena. And then, of course, one question when you study this manifold is, can I extend this construction to higher order simplicial complex? And the answer is yes. So we have done this with this emergent hypermolic geometry method. So this is all only in 2 dimensions, in which you stack triangle to link, but you can do also in 3 dimensions, in which you stack tetrahedra to triangle randomly. And on the other side, we have maximum entropy models. These are typically the equivalent of a random graph. So they are not geometrical in nature, while these NGF are very geometrical. So they can constitute a playground to study dynamical process on top of it. And so what is emerging from our understanding about the structure and the dynamics of higher order network is that, so far people have looked in the context of network only mostly on the combinatorial and statistical property, how the degree distribution shape the phase diagram of different processes, like epidemic spreading, percolation. But actually, in higher order network, also this interaction is also mediated by simplicial geometry and simplicial topology. So we started with this direction, and interesting enough, I was stimulated by a collaboration with a neuroscience group, which had experiments on neuronal culture, either grown on 2D slice or on 3D scaffold. And then they observed in this experiment that 2D is less favorable than 3D for promoting synchronization. And this burst a kind of research line in my group. And so we focused then on more theoretical results in the framework of the Kuramoto model, in which you have phases, a variable associated to the node at this time, and coupled to each other in such a way that despite the node have different frequency to start with, when they are coupled to each other, if the coupling constant is large enough, they start to synchronize together. And so this synchronization transition is captured by this order parameter that is 0 if there is no synchronization, and is greater than 0 if there is synchronization. So what we did is we look at this NGF, this network with geometry, because the question is if the dimension is important for the stability of the synchronization. Dimension. And the NGF have a spectral property that is called spectral dimension. If you look at the Laplacian, the density of the Laplacian for small eigenvalue increase as a power law. And this is something that occurs also in lattices, but for instance, never occur in a random graph. So this means that the relaxation time to equilibrium is dictated by a hierarchy of small eigenvalue, and not just by one smallest positive eigenvalue. So here the NGF allows us to tune this slope, this slope of this curve. And so we were able to prove a result that actually in order to have a stable synchronization, you need a spectral dimension greater than 4. And for the NGF, this occurs for dimension slightly above 3, greater than 3. So if you have the NGF, you see a fluctuation of the order parameter in time and also in space. And you can see a synchronization, but this is not thermodynamically stable in the sense that if you go to larger network size, is not there. And it will be thermodynamically stable only if the spectral dimension is above 4. Okay, so this is proof that the geometry can change the dynamical property of the network, and that the spectral dimension is the right notion for it. Then we went on and studied this other direction, how topology can change dynamical signal, dynamical effect. And so we were interested in topological signals, which, as I mentioned before, are dynamical variable not only associated to the node, but also to the links, for instance, or to the triangle of a simplicial complex. And example of these topological system signals exist in real system. So these are functions associated to simplices. Nice way to understand what they can be is a citation of a collaboration network where, you know, a team of people can have a given citation in their paper together. So it's not an individual citation record, but a collective one. Or you can have flux symbiotic transportation network, or a synaptic signal, or H signals in the brain as proposed by Olaf Spons recently. Or you can have also vector field. So for instance, speed of wind at given location or current at given location in the ocean. These are vector true, but you can have a tessellation of the surface of the Earth, and you can project this vector onto the tessellation and treat it as a signal associated to the link of your tessellation. So the question is, do these topological signals undergo collective phenomena? And in order to do that, to see if this is possible, we use some notion coming from topology. So in topology, you have that the simplices, so node, links, triangle, and so on, are oriented. Typically, you choose the orientation from the small labels to the largest label. And you can treat them as the element of a vector space. So you can do linear combination of simplices. And these are chains. So for instance, this is an example of a one chain, which is formed by 1, 3, minus 2, 3, and 2, 4. Okay. So with this linear chain, you can have operator acting on them. And so this boundary operator is very important. And when it acts on a simplex like a link, it gives you the two-end node, the output minus the input. If it acts on a triangle, it gives you the links at the boundary of the triangle with the right orientation. So you have 1, 2, 2, 3, and minus 1, 3, because you need to go in the anti-clockwise direction. So these boundary operators are nothing to be scared of. They can be just encoded into matrices. And so you have the B1 matrices, which have these are rectangular matrices. The B1 matrix has node as row and link as column. You have 1 and minus 1 here. And here for B2 as triangle as row and link as row and triangle as column. And you see here, this is the boundary of this triangle. So once you define these boundary matrices, you can combine them. And of course, it is interesting to see that the graph Laplacian, which I'm sure is one of the favorite operators for you, that describe diffusion on a graph, is just B1 transpose. And from this is apparent that lambda 0 is semi-definite positive. But you can also combine higher order boundary operator, describing diffusion, for instance, from links to links through node, or from links to links through triangle. While lambda 0 describes the diffusion from node to node through links, when you start from links, you can go through node or through triangle. And so you have this distinguish between lambda down and lambda up, and the dimension of the kernel of this higher order Laplacian is the n-Betty number. So it's really related to topology. And another important relation to topology is that this n-chain, like a signals or cochain, the signals defined on the links, can be decomposed in a unique way in 3 components. A gradient flow describing diffusion from a source or to a sink, harmonic component along the cavity, or solenoidal and curl flow. So interesting. So these topological signals are really good to study diffusion from simplices to simplices of a given dimension. But you can also have treat interaction between topological signals of different dimension. So for instance, you can treat node and link in signals in the same way. And this is done with the Dirac operator. So in the Dirac operator, you have a vector, which we call spinor, that has an initial block, which is the function defined on the node, the topological signal on the node. And the second block is the signals defined on the links. And then the Dirac projects the signals on the links into the nodes and the signals on the nodes into the links. So that actually the square of the Dirac is the Laplacian matrix, the diagonal Laplacian matrix. So you have L0 and L1 down. So you can, this is really interesting for people coming from physics, because this topological Dirac can be really used as a Dirac operator. So you can define a Dirac equation if you want. And you can visualize on real data sets the eigenvector of this Dirac operator. And so these are fungi network in which I did visualize this eigenvector. So you have function on the nodes and on the links. And this is another fungal network. And interesting, you can show that you can have eigenvalue of the Dirac that are either positive or negative, corresponding to matter-antimatter in physics term. And for any positive, you have a single negative eigenvalue. But this symmetry is broken if you are treating practically harmonic signal. In that case, the degeneracy of the corresponding eigenvector is given by the Betti number, and this doesn't have any equivalent in the classic Dirac equation. So you can also allow to have links and treat links of different types. So you can have a link in the X direction and a link in the Y direction, because you can allow when you project the signal from the link to the nodes, you can allow some rotation, additional rotation. And this might depend on which link are you treating. And this operation that you can do on lattices, you can do extend it also to a multiplex network, where also in that case, the structure doesn't have this nice tensorial decomposition, but in any case, you have link of 3 different types. If you have 2 interaction between the 2 nodes, or just one or just the other, and then you can treat this different type of multi-links in different way. So the topological Dirac, until now, we define only on node and on a network, but you can define it also on simplicial complexes. So you just take a bigger matrix in which you use B1, B1 transpose, B2, B2 transpose. These small number here are complex number with absolute value 1, which are reminiscent of this possibility of inducing a rotation in this space. And the Dirac, practically, when you have a signal, for instance, if you apply a signal defined on the link, you apply the Dirac, it will project it on the node and on the triangle simultaneously. So it can be used like that. And interesting, you have that you can study the eigenvalue of this operator, and you can have that you can have that the states, they can be decomposed into different bands, energy bands. So you can have state only localized on node and links, only links and triangles, or triangles and tetrahedra, and so on. So the question would be, can this eigenstate ever interact? And of course, for doing that, you would need a nonlinear term. So we are now using this Dirac operator extensively for treating topological signals. I will mention Dirac synchronization, but we are using it for Turing pattern, and we are using it for signal processing of topological signals as well. So it seems very abstract, but it is, I assure you, it's very useful. So let me just tell you about the Kuramoto model, and we have already introduced the Kuramoto model as formulated by Kuramoto in 1975. So you have a signals defined on the node, each node with its own frequency. So no synchronization if you don't have interaction. Then you turn on the interaction, and as the interaction meets the synchronization threshold, then you have this collective phenomenon. The question is, can we do the same if the signal is on the links or if it's on the triangle? And what does it change? So this is a work we have published with Anna Paula Millán and Joaquin Torres in 2020. So we want to treat this collective phenomena of topological signals. And the first thing that we realize is that the Kuramoto model, which I introduced to you with this adjacency matrix Aij, can be written equivalently with the incidence matrix B1, where theta is the vector of phases associated to the node, omega is the vector of frequencies, each one for each node, sigma is the coupling constant, and then here you take the sign function element-wise. So now the question is, how can we formulate the Kuramoto model for topological signals defined on the links, for instance, or on the triangle? And way to do that is by using the higher order boundary incidence matrices, and you couple link to link if they share a node or if they share a triangle. And this is a really higher order interaction in the sense that here in the argument of the sign function, you will find three phases associated to the tree link, for instance, in this example, and the convention of the sign is highly non-trivial, but only dictated by topology, only dictated by your boundary operator. So once you define your orientation of the links, and this orientation is to much extent arbitrary, because the spectral property of a simplicial complex do not depend on the labeling of the node, then you are done. You can close your eyes and you can write down the equation. And so the question is, now that we have defined the dynamics on the links, for instance, what is the projected dynamics on the triangle? What is the projected dynamics on the node? And the question is that we can do that by using the boundary operator again. So we can project the phase on the links by using Bn plus 1 transpose, which is the discrete curl, and we project it on the triangle, or we can do the projection on the node, and then we use the discrete divergence. So these two dynamics of these two projected dynamics are totally decoupled, and they lead to a synchronization at zero coupling of the two projected dynamics. But interesting, you will not be able to find the synchronization if you don't distinguish between these two components, which correspond to the solidonial and the irrotational component of the signal. So you really need this filtering. You really need the Hodge decomposition to reveal that. And this is a little bit like Fourier filtering. It's nothing very challenging, but it's something that you need to know, that you need to do it to observe that. So another thing that we have done is that we have coupled these two projected dynamics. So the dynamics which couples links to links through node is modulated by the order parameter of the projected dynamics on triangle and vice versa. So now when we study these two projected dynamics, these are not totally decoupled because one is the coupling constant is modulated by the order parameter of the other. And interesting in this case, then the synchronization become abrupt and explosive. So this is really interesting. And this is simulation on the configuration model of simplicial complexes. These are results on Homo sapiens connectome, which show similar effect, and C. elegans connectome. And so we went on and we explored different possibility. One first thing that we have considered is coupling node and link topological signals together. And the first thing we have done is the easiest thing. We have considered this global coupling, this global adaptive coupling. So we have multiplied. This is the equation for the node signals. This is the equation for the link signal. And we have multiplied by the order parameter of the other component of the dynamics. And in this way, you see you have the node signals, the link signals projected on the node, and the link signals projected on the triangle that all together abruptly synchronize at the same time. And this is both for this geometrical simplicial complex and for the configuration model of simplicial complexes. So we have a theory for that. So yeah, the analytical understanding is this black curve, which follow very well the backward transition. For the forward transition, we don't have the theory because actually this transition is not thermodynamically stable, so it moves to the right as the network size goes to infinity. And so, and we have also theory for the fully connected case. As I mentioned to you, we want to do even better, and we want to couple node and link signals, but in a way that is purely topological, not with this global order parameter, because one might argue that if there is a coupling between a node state and a link state, this coupling might not be dependent on the global state of the network, but also locally on the state of the nearby node or the nearby links. And in order to do that, we need the Dirac synchronization. And so on a network, we notice that we have node Kuramoto model, and then we have the link Kuramoto model. Now, only the coupling through the node is valid because we don't have triangle, we are a network. And in these two equations of node and link Kuramoto can be written in terms of the Dirac in this very easy way. But they are still uncoupled. So what we would like to do is we have done, we have introduced a phase lag on the dynamics of the node that depends on the dynamics of nearby links. And we have introduced a phase lag on the dynamics of the links that depends on the dynamics of nearby nodes. And we have defined this equation in which here we practically use a normalized Dirac to the power of 2. And we have studied this Dirac synchronization on a fully connected network. And this was the standard Kuramoto model, just node, the order parameter just for node. This is the link synchronization when you don't have this adaptive coupling, so at zero coupling. And then you work with the Dirac synchronization. And then what happens is that you have order parameters that are now not only depending on a linear combination of node and link signals, so they are coupled, intrinsically coupled together, and you have a discontinuous forward transition and a continuous backward transition. And this is this black line is our theory. So we have a theory that fits very well the simulation result in this case. In addition to this collective phenomena that we observe here is characterized by a very non-trivial rhythmic phase in which the order parameter oscillate, R alpha in particular, oscillates in the complex plane, forming a kind of a circle here. And as you raise the coupling constant, these circles start to have some wiggling and then disappear. So this is a way in which this rhythmic phase emerges only when the frequency that we impose on the node and on the links is zero. So also if we put ourselves in the framework in which the average intrinsic frequency of node and links is zero, still the network starts to have this oscillation, which are very long-lived. So they are very small frequency. So they very low rhythm.
Sorry, Ginestra, can you tell us again what X alpha is?
X alpha is
In the next, in the
alpha.
next slide, in the next slide. Yeah, the
X
X.
alpha is the complex order parameter.
Okay.
So R alpha is the
Oh,
absolute
got it,
value
got
of the
it, got it.
complex
Thank you.
parameter. Yeah. So X alpha, yes, is the sum of the exponential of the phase.
Thank you.
So I want to conclude this. So this is very, very interesting. And I think we are working on a sparse version of it, also the interplaying between this and topology. And I want to conclude this talk with another subject. I realize I run a little bit out of time, but let me see what can I say about this. Is very exciting work on this direction, how combinatorial and statistical property affect higher order dynamics. So here you have one node affecting the interaction between two other nodes. And this interaction can be positive or negative. For instance, you can have a species that enhance or inhibits the interaction between two species, or you can have a glia that change the synaptic interaction between two neurons. And we are playing with design, and we show that percolation can become a fully dynamical process. So percolation is the study of what happens when you remove links with a given probability, and then you look at the largest component that should be also extensive. So it should be of a number of nodes of the order of the network size. And then you monitor R as a function of P, the probability that you retain a link. And so as P is reduced, so you damage more and more node, you typically find a second order phase transition. This is the shape on a random graph, and these are the equations on the random graph. So this is very, very widely studied. So we consider this regulatory interaction, which can be positive or negative. So we have nodes and links, but then some of these nodes can regulate this link. And this regulation can be positive or negative. So we assume that structural links are active if they are connected to at least one active positive regulator node, and they are not connected to any active regulatory node. And then structural interaction determines which node are active. A node is active, it belongs to the giant component of a network. There are minimal assumptions. So we consider a dynamical version of percolation in which at step one, we evaluate the giant component of a network, and the nodes are active if they belong to the giant component. And at step two, we deactivate the links that are connected to at least one active negative regulator node, or that they are not connected to any active positive regulator node. And then we induce also some stochasticity. And so all the other links are damaged with probability 1 minus p, much like in standard percolation. And then we repeat from step one. So this is an example of a toy model. We start from all the nodes connected, then this node is down-regulating this. So at the step two, we damage this link. So since this link is damaged, at the next step, this node is removed, and so on. And we notice that at time t equal to 2, we find the same configuration that at time t equal to 4. So this approach induces blinking. So the network is switching on and off in time. And so we have a theory for that. So these are the equation for percolation. This is the equation for regulation. And these are like two map, one in which, given the probability that you have to retain a link at time t minus 1, you calculate the probability that a node is in the giant component at time t. And the other equation is that given the probability that the node in the giant component at time t, you calculate the probability that the links are retained. So when you study these maps, you see that indeed you can observe this period 2 oscillation. So the order parameter, this is the order parameter of percolation, which is oscillating in time, which means that you have something like this. This is a visualization of that. So the network, the link, and the activity of the node is oscillating in time with period 2. And you can also have period 4, and you can also have chaos of the order parameter. So what happens is that the network the connectivity can really change in time in a chaotic fashion. Okay, so this is really shown that this phase transition that I mentioned to you for percolation, which was this nice second order transition, become an orbit diagram in which you can have discontinuity, period 2. So for a given probability to retain the link when all the constraints are, so this is the probability of stochastically retain the link. You can have period 2, you can have period 4, and you can have chaos. And this is the theoretical prediction, just with 3 equations. And these are the Monte Carlo simulation for 10,000 network of 10,000 nodes, and in which, of course, each link is a degree of freedom, and in which there is also stochasticity, while these equations are deterministic. So given that, the agreement is really fantastic. We have seen that these phenomena can occur also not only on random graph, but also on real network. For instance, we took the mouse brain network plus random regulatory interaction, and we find this complex phase diagram. And finally, we have a theory and an explanation that actually this dynamical aspect of this percolation is only observable when you have negative regulation. When you have positive regulation, you typically reach a steady state. Interesting, the transition is not continuous but discontinuous. But still, you don't have any more this dynamical effect. So it has been probably a long journey. I believe. I'm sorry if I was the talk was containing too much information, maybe. But I think I wanted to show you that higher order interactions are really ubiquitous in complex systems, and they are characterizing the combinatorial, topological, and geometrical property of higher order networks. And this can really change our understanding of dynamics. Hopefully, this progress or this research line could be of some advantage for neuroscience. And so higher order dynamics display unexpected phenomena, including this topological higher order synchronization and this percolation in presence of triadic interaction. And really, I want to point to you this operator, the Dirac operator, which is really very fun to work with. And well, it can be considered the equivalent of a derivative for your network, and it allows this projection of topological signals in different dimension. And so thank you so much for your attention, and I'm here for questions.